Welcome to our discussion on curve sketching. Now, as before, I've talked about how taking derivatives can be used to aid in sketching a curve, and that's not really the most important application of it. We can sketch curves far more accurately with technology. The idea is to use curves to kind of help us see what derivatives tell us about a function. So we're going to go through a bunch of steps on how we could sketch curves by hand. And I know you're going to think, why are we wasting our time with all of this stuff? The goal is not so that we can sketch a curve, because we can do that with technology. The goal is to understand more about the function from its properties. And you can discover its properties by going through all of these steps that would then enable you to sketch it. So it's really more about understanding what the function is. So the first thing you want to look at is the domain. Right? What's the domain of the function? Where is it defined? Most of the functions we're going to deal with are defined everywhere, but that's not always the case. The next thing you're going to look for are the intercepts. It's always very important to know, when does the curve cross the x and y axes. So set x equal to 0, right? And then that's how you find your y-intercepts. And then set the function equal to 0, i.e. set y equal to 0. And that's where you find your x-intercepts. Those are very important things to know for functions. Then determine if your function is symmetrical or not. Does it have symmetry? Is it an even function where it's symmetrical around the y-axis, right? Where we have f of negative x equaling f of x, and that tells us a lot about the function. Or is it an odd function? Well, if it's an even function, you know that you only have to worry about what's happening on one side of the y-axis, and the other side is going to be the same. And there are a lot of typical functions that we deal with that are even functions: cosine, absolute value, even powers of x, squared, fourth, sixth, eighth, etc. For odd functions, we know that when we plug in negative x, we get a negative answer, right? So f of negative x equals negative f of x. You plug in a 2, you get an answer of 7. If you plug in a negative 2, you get an answer of negative 7. If you plug in an answer of 5 and you get an answer of negative 3, then negative 5 has to go to positive 3, right? That's an odd function. Again, it helps us with graphing, but it's more helpful to just know that that's what our function does. And some typical examples are sine and then the odd powers of x, the 1 power cubed, fifth, and so on and so forth. Okay, well, maybe they're not even, maybe they're not odd, but maybe they're periodic. They repeat, like sine and cosine. But there are also other periodic functions. A picture of the one below. If it's periodic, then it's really good to know what the period is. How often does it repeat? So for sine, for instance, has a period of 2 pi. Tangent has a period of just pi. Those are important things to know about your function. Next, asymptotes. Does it have a horizontal asymptote? Well, again, that's more telling of what the function does at the extremes, right? A horizontal asymptote just tells us what are the values we're going to get out of this function at the ends, right? Way out at infinity or way out in the other direction at negative infinity. So that's the importance of a horizontal asymptote. And same thing if it doesn't level off. It's good to know that the function just continues to grow, right? Gets super large or super small in one direction or the other. Vertical asymptotes are very important because they really tell us where the function is undefined. And then it's also good to know what happens on each side of that point of discontinuity. Does the function blow up to infinity, or does it go down to negative infinity on each side of your vertical asymptote? Those are important things. Last, we have slant asymptotes. And remember, we find slant asymptotes the exact same way that we find regular horizontal asymptotes. And it's just that slant asymptotes only occur when we have a rational function where the degree of the top is 1 degree bigger than the bottom, or in some other cases where we have other types of functions where we do the same kind of limiting idea, and it's left with, after you do some algebra, basically a linear function, a y equals mx plus b, and then plus some remainder that goes to zero, right? That remainder has to go to zero as you go out to infinity or to negative infinity. After asymptotes, we look at the intervals where the function is increasing and decreasing. Again, can be very important. If it's a profit function, you definitely want to know when your profits are increasing versus decreasing. And if it's a cost function, same thing. And the easiest way to do that is to use the increasing decreasing test, which is really just a matter of taking the derivative, right, f prime of x, and then finding when the derivative is positive and negative, because that tells you when it's increasing and decreasing. So that's a simple, easy test. Then we want to find local mins and maxes, also very important for our functions. Also done very easily with first derivatives and using the first derivative test. You can always use the second derivative test if you like, but I tend to believe the first derivative test is easier and quicker and cleaner in almost all circumstances. It's very rare where the second derivative test is better. Next, you want to check concavity and points of inflection. So you do that with the second derivative. You take the second derivative, and if it's greater than zero, you know it's concave up. And if it's less than zero, it's concave down. Those are nice and intuitive, right? Greater than zero, up, less than zero, down. That's nice for concavity, but it's counterintuitive for max and mins, which is another reason why that second derivative test can be a bit of a bother compared to the first derivative test. And then last, of course, we're going to talk about we can now sketch the curve by plotting the points, plotting our asymptotes, putting in dotted lines for verticals and horizontals or slants, and then plotting all of our intercepts, all of our maximums, all of our minimums, all of our inflection points, all those important points, critical points that we found. And then it's basically just connecting the dots with smooth curves. But remember that last part, H, is really the least important part of all of this. It's really all about learning something about your function from A through G. Let's look at a couple examples. So here's a typical rational function. First thing we do is check the domain. We start with all real numbers because it started with polynomials, but because it's rational, we have to worry about the bottom being equal to zero. We set the bottom equal to zero, solve for that, and we realize that the domain is going to be everything except for minus 1 and 1. All right, checking for x and y intercepts. That's where we let x equal 0, and we get an answer of 0. And then we set the function equal to 0, and we also get 0. So the only x and y intercepts are basically at the origin, 0, 0. Now we check for symmetry. If you plug in a negative x, you'll get the exact same thing because you notice that all you have is an x squared and an x squared right in there. So it's going to be symmetrical around the y-axis. We look for our limits, what happens at plus and minus infinity. So we use our simple trick of dividing by the highest degree of the denominator, in this case x squared. Divide everything by x squared. Then take the limit, the 1 over the x squared piece goes to 0, and you're left with 2 over 1, which is 2, and so therefore we have a horizontal asymptote at 2, which just tells us this function levels off at 2 at plus and minus infinity. Now, since the denominator is 0, regardless of whether or not x is plus or minus, we can compute the following limits as we get closer to those points of discontinuity, right? The plus and minus ones from our vertical asymptotes, and we can figure out does it go up to infinity or down to negative infinity on each side of 1 and minus 1, and the results are there. Now that we've gotten to that point, we've gone this far, it's a good idea to kind of give a rough sketch of what we found so far. So you plot your asymptotes, your vertical and your horizontal asymptotes, and then you just make little tick marks to tell you what's going on. From our investigations, we know that it goes up to infinity as we approach negative 1 from the left, and we know that it goes up to infinity as we approach positive 1 from the right, and then we know it goes down to negative infinity as we approach negative 1 from the right and positive 1 from the left. So that's what these little tick marks are. And then we know that the function levels off at 2 in both of those directions, and in fact we can also figure out that it's always greater than 2. And that's why these marks are above instead of below. It also kind of makes sense that since it's a curve, don't you think this point is going to have to eventually touch that point? Now that does, remember horizontal asymptotes, it can cross, so it could go below it, come back up, and level off underneath it. So that's something you have to check when you're doing those horizontal asymptotes. But that'll come out when you're looking for mins and maxes, local mins and maxes. Because if this drooped down and came back up, wouldn't you have a local min down here? And then you would also have a local max up here. Unless it leveled off like a logarithmic curve, it most likely would kind of bump up and then level off. So you can find curves that way. Okay, the next step, E, we take the first derivative and we figure out when it's equal to 0 to find critical values. The only time it's going to equal 0 is when x equals 0. So we found that same critical value that ends up being our intercepts. We also look to when the derivative, remember, is greater than 0 or less than 0, and that tells us when it's increasing and decreasing. So we can find the intervals where it's increasing and decreasing. And based on when it's increasing, decreasing, and our critical number, we now know that the number 0, 0, the origin, is a max. We go to the second derivative, take the second derivative. We can see that the top is always greater than 0, right? Because right now we're looking for concavity, so we're worried about when the second derivative is greater than 0 or less than 0. We're also looking for when it equals 0, because that gives us points of inflection. But since the top can never equal 0, the function itself can never equal 0. So now we're just looking at plus and minus, right? When it's positive, when it's negative. Top is always positive, so then we're worried about when the bottom is positive and negative. Well, since it's being raised to a power of 3, that's going to be positive whenever the stuff inside is positive and negative whenever the stuff inside is negative. So it's going to be positive whenever x squared minus 1 is greater than 0, which means whenever x squared is greater than 1, which means whenever x, right, the absolute value of x is greater than 1, or x is greater than 1 or less than 1. And then conversely the other way. If you were to graph this function, we know that this is x squared, right? What does x squared minus 1 do but shift it down? And so you can see the function is negative on this interval and then positive out here, right? So it's positive on the red intervals and negative on the x intervals. So it's concave down, right, on the black intervals and concave up on the red intervals. Now we can connect all those dots. Remember, we started with just some initial tick marks. We had a little tick mark here and here and here and here and down here and down here. Then we plotted our intercept. It also ended up being our maximum. And we connect those dots and we get a rough sketch of what the function looks like. Again, not the most important part. The most important part is all the information we have learned about our function. All right, slant asymptotes, remember, as they're sometimes called oblique, and I mentioned that this is when you take the limit as you go out to infinity or negative infinity, you get a straight line and a remainder. For rational asymptotes, this only happens when the numerator is 1 degree bigger than the denominator, and in order to find those, you have to do long division. So let's look at this example. We see that the top is 1 degree bigger than the bottom, so we will have a slant asymptote here. First thing we do is we look for the domain. The domain is going to be all real numbers, because remember, we just can't divide by 0, but x squared plus 1 is never equal to 0, so we're good to go there. We check for our intercepts. We let x equal 0. We get an answer of 0. We set the thing equal to 0 and solve, and we also get the same answer. And we get that origin again as our only intercept. Because f of negative x equals negative f of x, in this case, it's an odd function because of that x cubed on top, right? The bottom always gives us the same number, but the top always ends up giving us the exact opposite number. Now, again, since the bottom was never equal to 0 when we were looking at the domain, we also figured out that there are no vertical asymptotes. By doing some long division, we can see that as x goes out to infinity, the function ends up looking like x. And if you don't remember how to do your long division, you're basically just taking x squared plus 1 and putting it into x cubed, right, plus 0x squared plus 0x. Alright, x squared and x cubed has to be multiplied by x. This gives you x cubed plus x. You subtract, these go away, and you get negative x. X squared can't go into negative x. Right? So this thing can't divide into that. So this ends up being your remainder. So when you divide these two things, right, when you take x cubed and divide by x squared plus 1, you get x plus the remainder, which is the negative x over the original dividend, right? So you have this much left over, but that much is still being divided by x squared plus 1, and that's where this second piece comes from. Then you figure out what happens as you go out to infinity, and you use that same trick of dividing top and bottom by the highest power of the bottom, which in this case is x squared, and that's why you get this thing down here with the 1 over x and the 1 over x squared, which when you take the limit, those all go to 0. You get 0 over 1, which is 0, and so you're left with just x, and then y equals x is that slant asymptote. Next we take the derivative, get this, set that equal to 0 and solve. We can see that we have a 0 works, and then nothing else, right? This never equals 0. And then you check to see when it's positive, when it's negative, and you see that the derivative is greater than 0 for all x except for 0. That's where it equals 0. And since it's always positive, then it's always increasing everywhere. And even though we have this critical number of 0, it's not a max or a min because it's increasing on the left and increasing on the right, so it's really just an inflection point. Take the second derivative, get this thing, again set equal to 0 and solve. The only answer you get is 0, and then in this case square root of 3, plus and minus, right? So there are our three critical values. We divide up the number line by those three critical values, negative root 3, 0, and positive root 3, and then we check, we do test points in each of those, right? Remember, this is very similar to the first derivative test where you've got negative root 3, 0, root 3, and then you just pick something in each of these intervals and test it in the second derivative to figure out when it's positive and when it's negative, and that tells you when it's concave up and concave down. So you take something smaller than negative 3, sorry, smaller than negative square root of 3, so, oh, I don't know, negative 2. This would be negative, right, because now we're just concerned with our three terms. So this one would be negative. If we plug a negative 2 in here, it becomes 4. That's negative. Put a negative 2 in here, positive, right? That's positive. So the whole thing ends up being positive. We see it's concave up on that interval. Repeat the process. In between the two, I'd pick negative 1, I'd pick a positive 1, I'd pick a positive 2. Check, 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 check. You get all the places where they're concave up and concave down. Now we can put everything together. We found that one inflection point at the origin. We had the other two inflection points at plus and minus root 3. We saw that it was concave down and concave up. And I know it doesn't look like it in the picture, but I'll write them down here so you can see it. Right? It's concave up here, then concave down, concave up, concave down. So it goes up, down, right? So on this picture, in this interval here, concave up, concave down, and then on this interval here, right, concave up, concave down. Well, this one's very obviously concave down, that one's very obviously concave up, but it's very hard to see that this is concave down and this is concave up. But because you have that slant asymptote, you know this thing is increasing, but it's also leveling off, right? So that's why it has this bend to it. You can't really see it, but it is leveling off. And then same thing here, it's decreasing, but it's leveling off. So that's why it's concave up. Again, we really don't care about being able to graph these things by hand, but it does tell you a lot about your function. It does tell you where your inflection points are, which, remember, an inflection point, concavity also tells you that the rate of increase of your function is either increasing or decreasing. Okay? If something is concave up, it's increasing at an increasing rate. So it's growing faster and faster. If something is concave down, it's slowing down. So even though the function is increasing, it's increasing at a decreasing rate. So that marginal increase, that next step, every time you go up by one unit in the x direction, you are still getting an increase in your y direction, but it's a smaller increase each time. It's kind of that law of diminishing returns idea. You're getting an increase, but you're getting a smaller increase each time. And sooner or later, based on your costs, that next step is not going to be worth it because the increase is no longer going to be big enough to offset some increase you have in cost. So the idea of concave up and concave down can actually be quite important, a lot more than just graphing a silly function. Okay? That's everything we need to know about curve sketching.